Good afternoon. Today I'm going to explain about Thumb symbol. I'm going to give you two different examples. The first example is about a situation that you have only one electron in p orbital. The second example is a little bit more complicated. You have four electrons in p orbitals. I'm going to show you for each case how to determine Thumb symbols of different energy levels and how to determine their relative energetic stabilities based on the Hund rule. So let me start with the P1 system, where you have only one electron in a p orbital. We know that for p orbital, you have three different magnetic quantum numbers, -1, 0, and 1. So three different p orbitals are at the same energy level. So the maximum number of electrons which can go into p system with the same principal quantum number is 6, right? In each orbital, in each p orbital, you can put maximum 2 electrons. And there are 3 p orbitals at the same energy level, maximum 6 electrons. First, let me start with number of microstate. So number of microstate can be determined by this equation. Number of microstate is maximum number of electrons in given orbitals, factorial, divided by number of electrons factorial divided by number of holes factorial. So in 3p orbitals, you can put maximum 6 electrons, so 6 factorial. Right? This is 6 is maximum number of electrons which can go into p orbitals with the same energy level. So 6 factorial divided by the number of electrons. Now we consider only one single electron, so 1 factorial divided by number of holes. So this is basically the number of unoccupied site, which is 5, right? So number of microstate is 6 factorial divided by 1 factorial divided by 5 factorial. It becomes then 6. We have 6 different microstate for the situation having only one electron in a p orbital. Now let me go into details how each of these 6 microstate should look like. Well, you can put one electron either in a p orbital with magnetic quantum number of -1, 0, or 1. And you can either put your electron as spin up or spin down. So two different spin state and three different magnetic quantum numbers, then you come up to 6 different microstates. So spin up, spin up, spin up, electrons to different p orbitals with different magnetic quantum numbers, spin down, spin down, spin down. Okay, again, 3 different electrons going into 3 different p orbitals with different magnetic quantum numbers. So 6 different microstate in this case. Now, this kind of microstate array of microstate can be converted into this kind of table. Now, in this table, what you can see is here the sum of magnetic quantum numbers. I mean, here we have only one single electron, so basically the magnetic quantum number of an electron is the same as sum of magnetic quantum numbers. But of course, later on, we are going to consider multi-electron system. If you have 2 or more than 2 electrons, then the magnetic quantum number of each electron should be then summed up to get this value. But in this case, now we have only one electron, so sum of magnetic quantum number is the same as magnetic quantum number of that electron. That can be either -1, 0, or 1. Again, for spin quantum number, sum of spin quantum number is given here, but we have only one single electron, so spin quantum number of that electron is the same as sum of spin quantum numbers. So again, when you consider 2 or more than 2 electrons, then the spin quantum numbers of multiple electrons should be summed up to calculate actually these values in the table. But now we don't need to consider that. Anyhow, the spin quantum number can be either half or minus half. For example, consider the microstate numbered with 1, you have spin quantum number of half, right? Spin up, spin quantum number of a half, spin down, quantum number of minus half. So here you have spin quantum number of a half and magnetic quantum number of minus 1. Okay, so magnetic quantum number minus 1, spin quantum number of half. So this microstate should be assigned to this block of the table. We can do the same thing with another microstate. Probably we can do that with microstate number 6. Here you have spin quantum number minus half because it is spin down. And now magnetic quantum number is minus 1. So minus 1 minus half. Minus 1 minus half. So number 6 microstate should be attributed to this block of the table. So if you do that for all 6 microstate, then you can see that each microstate can be then assigned to each block of the table. So you fill each block of the table and then you come up to this. Now that means that all these microstates can have the sum of magnetic quantum numbers of either minus 1, 0, or 1. And some of the spin quantum number can be either plus half or minus half. Okay. Now, for p atomic orbital, we know that for p atomic orbital, the magnetic quantum number is minus 1, 0, 1, and the angular momentum quantum number is 1. So, similarly, if sum of ml, magnetic quantum number, which is given to be here capital ml, I told you already that we have only one single electron, so magnetic quantum number of electron and sum of magnetic quantum numbers should be the same in this case. So here the small ml and capital ml should be the same, which are going to be different actually later for multi-electron system. Anyhow, so the sum of ml, the capital ml, is minus 1, 0, and 1 in this case. Okay. So if small ml would be minus 1, 0, 1, then small l would be 1. So if capital ml would be minus 1, 0, 1, then the total orbital angular momentum, capital L, should be 1. They have some analogy, right? We have seen that when angular momentum quantum number would be 0, 1, 2, 3 for atomic orbital, we use the symbol as PDF for each angular momentum quantum number. For total orbital angular quantum number, capital L, being 0, 1, 2, 3, we use the symbol capital as PDF. Okay. Now for electron, spin quantum number is either plus half or minus half. In this case, small s, the spin quantum number is half. If sum of ms given as capital MS would be plus half or minus half, likewise, then capital S, the total spin quantum number would be a half. Now we can calculate 2s plus 1. For an electron, 2s plus 1 is 2 because s is half. If capital S would be a half, then 2 capital S plus 1 would be 2. This 2s plus 1 is 2s plus 1, and that is called spin multiplicity. Okay. So how do we make a thumb symbol? We know that now L is 1 from this table because the capital ML would be minus 1, 0, 1. So L should be 1 in this case. So L1 should have the capital P as symbol. Okay. Spin multiplicity is 2 in this case. So this 2 spin multiplicity should go to the upper left side. Okay. So we come up to this kind of symbol from the L, capital L and capital S provided from this table. Okay. Now we have now then the J value. J is the constant representing the spin orbit coupling. So L plus S L plus S minus 1 minus 2, it can go up to L minus S. Okay. Now, in our case, in this table, L is 1 and capital S is half. So L plus S is 3 half, L minus S is 1 half. So this J value can go to the right side of the symbol as a lowercase. So ultimately, we have two different Thom symbols derived from this table, 2p 3 half and 2p a half. These are two Thom symbols derived for one electron system in a p orbital. Okay. We have derived these two different Thom symbols, okay, each one representing each energy level. These are Thom symbols. L plus S to L minus S, this J value, either half or 3 half, yeah? These are J representing the spin-orbit coupling. So orbit correspond to the angular motion. An electron is making angular motion around nucleus, okay? On the other hand, electron has also spin, okay? And either it can make angular motion anti-clockwise and also spin anti-clockwise, or it can make angular motion anti-clockwise but spin clockwise. They can be energetically separated, corresponding to 3 half and a half. So different spin-orbit couplings are represented by this J value, which can be found actually on the right side as a lowercase, the Thom symbol. 2J plus 1 correspond to the degeneracy of each energy level represented by the Thom symbol. So here 3 half, J 3 half, 2J plus 1 becomes 4. It has degeneracy of 4, right? So likewise, you can come up to the conclusion that this should have degeneracy of 2. So you have 2p 3 half having degeneracy of 4, and then 2p half having degeneracy of 2, right? Now, we started with 6 different microstates, and we come up to 6 new states, 6, 1, 2, 3, 4, 5, 6, 6 new states represented by 2 different Thom symbols. So basically, we start with 6 different microstates, and then you reorganize them, and then you come up to 6 states, but separated at 2 different energy levels. Okay? And the system does it to minimize the energy. Basically, it is very similar to the situation that you make a molecular orbital or the atomic orbitals. You start with 2 atomic orbitals, you combine them together, you come up to 2 molecular orbitals, bonding orbital and anti-bonding orbital. So when you start with a certain number of base set, each one representing each state or each wave function, you reorganize them and you come up to the same number of states, but organized differently. And the system does it to minimize energy. Okay, now we learned that 6 microstate for the system having only 1 electron in a p orbital can be reorganized into 2 different energy levels, one having a degeneracy of 4 and the other one having degeneracy of 2. And now the last question you have to answer is actually which one is lower in energy and which one is higher in energy. For that, we have to apply Hund rule. So Hund rule. The Thom, there are 3 different rules here. The first rule, the rule with the highest priority, is that the Thom with the largest spin multiplicity plus 1 is the most stable one or lowest in energy. The spin multiplicity is this one. Okay, so the larger this number, the lower in energy. But in this case, both have the same spin multiplicity. So the rule number one does not give us clue about which term symbol would be representing more stable energy state, energy level. So in this case, we have to go to the second rule. The second rule is that for terms with the same multiplicity, same spin multiplicity, the one with the larger total orbital angular momentum is more stable. So SPDF corresponding to the total orbital angular momentum of 0, 1, 2, 3, the energetic stability should increase like that. So F should be more stable than D should be more stable than P should be more stable than S. But in this case, again, both are P here. This is P, so we cannot even determine which one is more stable based on the second rule. So then now we have to go to third rule. For a given term, same S and L, we have to think about two different situations. The number one, when the shell is less than half filled, okay, we have maximum 6 electrons in p orbitals with the same principal quantum number. So half is 3, and we have only 1 electron. This is the situation corresponding to ours. We have only 1 electron in p orbital, so less than half filled. The level with the smaller j is more stable. So half, 3 half, smaller j is more stable. So this is more stable. So this is the reason why I drew actually the energetic diagram like this. But when the shell is more than half filled, the level with the larger j becomes more stable. Okay, so this is what you're going to see with 4 electrons in p orbitals. So there are some qualitative justifications about these 3 different rules. Number one, regarding the spin multiplicity, this is the first rule I introduced you. Regarding this first rule, electrons having the same spin means that the magnetic field generated by their spins are aligned in the same direction. So basically, largest spin multiplicity means that if you have 2 or more than 2 electrons, then they have the same spin, right? Uh, This magnetic alignment increases the average distance between electrons. So you have 2 small magnets aligned along the same direction. Okay, due to this magnetic coupling, the average distance will become larger. And this minimizes the Coulombic repulsion between them. The magnetic coupling of the electrons with the same spin increases the distance, but this actually decreases the Coulombic repulsion, and therefore the system becomes more stable. So regarding the second rule, yeah, a larger total orbital angular momentum L means that electrons occupy orbitals with larger magnetic quantum numbers. Electrons with a very different magnetic quantum number values tend to have greater overlap in their electron densities, whereas electrons with larger and similar ML values have reduced overlap. Of course, if electrons would have more overlap, electron densities would have more overlap, then they would have more repulsion. If they would have less overlap, then they would have less Coulombic repulsion and become stable, more stable. Electrons with large and similar ML values are like sitting at opposite sides of the same table, keeping their distance from one another. So everything is about reducing the Coulombic repulsion by making the distance between electrons as far as possible to minimize the energy and make the system more stable. When the orbital angular momentum and spin magnetic moment are oppositely aligned, the total angular momentum is minimized. However, when a shell is more than half filled, the interaction between the electron's angular momentum and not the electrons but hole becomes dominant, causing the rule to reverse. And that is the reason why the rule for the situation having electron less than half and more than half are just reversed. Okay, this is about the Hund rule. Now we go to a second example, a little bit more complex example, where we have 4 electrons. But basically, we have more microstage, yeah, than in the previous situation. And you have more Thumb symbols, more stage, more energy levels, more Thumb symbols. But the basic idea to make some tables from the possible microstage and then attribute each table to some Thumb symbols, and then application of the Hund rule to determine the relative energetic stabilities of different energy levels, that is basically the same. Okay, let me go to the system where we have 4 electrons in p orbitals. Number of microstate, again, 6 factorial, number of maximum electrons in given orbitals. We are still talking about p orbitals. Well, maximum 6 electrons can go into p level, so 6 factorial. And now divided by, now we have 4 electrons and 2 vacancies. So 6 factorial divided by 4 factorials and 2 factorials. So we come up to 15. So we should have 15 microstate. Now you see all 15 microstate here. The only thing you should be very careful about is that the Pauli exclusion principle should be, that is a law that should be obeyed. Okay, so you cannot put 2 electrons like this. That is impossible. Okay, so beside that, you can think about all different possibilities. Then you can come up to 15 different configurations for having 4 electrons in p orbitals with 3 different magnetic quantum numbers. I don't want to go into too much details, but probably you can check whether, or you can try to reproduce actually this 15 microstate and check your own result with mine, whether they agree with each other very well or not. Okay, so anyhow, 1, 2, 3, 4, 5, 6, 7, 8. 9, 10, 11, 12, 13, 14, 15. So we have 15 different microstates. Okay, and that is exactly the same as the result of the calculation based on this formula. Again, I have to emphasize Pauli exclusion principle. That is a law that should be obeyed. Okay. All right. So first, I bring only this part. This 8 microstate again in the next page. Okay, and then make a table. Now, because we have more electrons, the sum of the magnetic quantum numbers can be either -2, -1, 0, 1, 2. The sum of the spin quantum numbers can be 1, 0, -1. If you calculate the sum of the magnetic quantum numbers of all electrons in a given microstate, and also sum of the spin quantum numbers, uh, for all 4 electrons in a given microstate. And if you do that for all 15 different microstate, then you are going to see that the sum of the magnetic quantum numbers of 4 electrons in a microstate, capital ML, can be either -2, -1, 0, 1, 2, and capital MS can be either 1, 0, and -1. Okay, let me just pick up 2 different examples and try to calculate the capital ML value and capital MS value. So in this case, okay, these 2 electrons have, each of these 2 electrons has magnetic quantum number of -1. These electrons have magnetic quantum number of 0. So for this, capital ML should be minus 1, minus 1, minus 1, minus 1, 0, 0, 0, plus 0, plus 0. That should be minus 2, right? Okay. Now, regarding spin quantum number, sum of the spin quantum numbers, plus half, minus half, 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 plus half, minus half. That should become 0. Okay. Then minus 2, 0. This microstate should go into this block. I think there is some mistake here in this figure. This block, not this block, but this microstate should go to this block. Okay. So a second example here, noted with green. ML value minus 1, minus 1, 0, 0, minus 1, plus 0, plus 1, 1, right? 1 plus 1, 1, 1. Magnetic quantum number minus 1, 0, 1, 1. Okay, that should be 1. Spin quantum number. Spin quantum number. Plus half, plus half, plus half, minus half. Plus half, plus half, plus half, minus half. Okay, there should be 1. 1, 1. Okay, 1, 1. This should go there. Okay. So we find one microstate corresponding to this block of the table. Another microstate can be attributed to this block. You can do that for all 8 different microstates. Okay. No, no. Oh, I think I made some. Yeah, I think everything is fine. Okay. So minus 2, 0 here, and then 1, 1, 1, 1. Okay. So I only try to find out the capital ML value and capital MS value for 2 different microstates, but you can do that actually for all 8. Then you can make your table like this. Okay. And then you can add, and this is only about half of the whole story. So I only consider these 8 microstates, but there are 7 more microstates. They are coming later. So there are 7 more microstates. And if you calculate also the capital ML value and MS value for each microstate given here, then ultimately you come up to this kind of table. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So you come up to a conclusion that 15 different microstates can be assigned to any block of this table. Okay. Now, this table can be now splitted into 3 different tables. Now, what you have to do is that you have here, well, 2 different microstates corresponding to this block, 3 different microstates corresponding to this block, 2 different microstates corresponding to this block. You have to make table as in a way that in every table you have only one single microstate corresponding to each block of the table. Okay? So you can do it by splitting your table into 3 subtables. Okay. So when you split this table in a way that in each block of your table you have only a single microstate, then you can come up to the conclusion that your table, this table with a 15 microstate can be then separated into these 3 different microstates. Okay. So if you add all three up, it becomes the same as the table we have seen previously. Okay. Now, here the ml value is 0, ms is 0, so L is 0, S is 0. When L is 0, then it corresponds to capital S. Okay. So capital S. And then 2, 2s plus 1 spin multiplicity, S is 0, so 2s plus 1 is 1, right? And L is 0, S is 0, then L plus S, L minus S, they are all 0, so you should have 0 here. This is the term symbol representing this table. Okay. Now in this table, you have S 0. The only ms value is 0, then S should be 0, right? But on the other hand, ml is minus 2 to 2. This is like, atomic d orbital. Then L value should be 2 as well. Then, as I told you, L 0, 1, 2, 3. 0, 1, 2, 3, SPDF. If L would be 2, then the main symbol should be D. Okay. And then here 2s plus 1, spin multiplicity, spin is 0, so spin multiplicity should be 1. Okay. And now if L would be 2 and S would be 0, the only J value is 2. L plus S, 2, L minus S, 2. Right. The third table, this is the most complicated one. Now ml value is from minus 1 to 1, minus 1, 0, 1. That means that L can be 1, right? So ms is minus 1, 0, 1, as you can see here. Then S should be also 1. Then, okay, if L would be 1, then you should have P as the main body of the term symbol. Spin multiplicity, 2s plus 1. In this case, if S is 1, then 2s plus 1 is 3. So you have 3 here. And then L1, S1 from L plus S to L minus S. L plus S is 2, L minus S is 0. So 2, 1, 0. All three different J values are possible in this case. So summarizing, from the 15 microstate, for each microstate we calculated capital ML and MS, which are the sum of the magnetic quantum numbers of all electrons in a given microstate, and the capital MS, which is the sum of the spin quantum numbers of all electrons in a given microstate. For all 15 microstates, we calculated capital ML and capital MS, and we completed this table. This table is then now separated into 3 different tables, okay? And from each table, we can determine capital ML, capital MS, then L and S can be determined, and for each table, we can determine the term symbols like that, okay? So these term symbols are given here. These term symbols are given here. Now, we have to determine which one is more stable and which one is less stable in energy. Okay, before going into the energy, we have to first decide the degeneracy. So these are J values, okay? Then we have 2J plus 1 degeneracy. You have degeneracy of 1, okay? You have degeneracy of 5, and you have degeneracy of 5, 3, and 1, okay? So 1, 5, 5, 3, 1. If you add them all up, 1 plus 5 plus 5 plus 3 plus 1. So if you add all them up, then it becomes exactly 15. So we started from 15 microstate. We started from 15 different microstates, and then we end up with now 15 different states with 5 different energy levels. So these 15 microstates, original microstates, they are reorganized into 5 different energy levels. Some of them has some degeneracy, so the total number of states becomes the same as the number of original microstates, which is 15 in this case. So now we have to determine which one is more stable, which one is less stable in energy. So we have to apply Hund's rule. The first rule was about the spin multiplicity. Here you have 1, 1, 3, 3, 3. The larger the spin multiplicity, the lower in energy. So all these 3 should go lower than these 2. Okay. Now, the second rule is that the larger the total orbital angular momentum, the lower the stability. So this rule can be applied to determine which one between these two should be lower in energy and which one is higher. So here D L is 2, for S L is 0, 2 is larger, and this is lower in energy. Okay. So now these are lower than these two, and between these two, this is lower in energy and this is higher in energy. But now we have to determine then at the end the relative energies of these 3. Okay. Now we have to apply J value. Okay. Now let me go back to the page where I already explained about the Hund rule. This is a situation where we have more than half field. We have 4 electrons, so this rule should be applied. Now we have more than half field situation. The level with the larger J is more stable. So 2 is more stable than 1, 1 is more stable than 0 energetically. So we come up to the conclusion that 2 is the most stable one, the next stable one is 1, and the least stable one among these 3 p-term symbols represented energy levels is 3p0. So, well, summing up, first, from the spin multiplicity rule, we decide that these are lower in energy and these are higher in energy. From the total orbital angular momentum rule, we determine this is more stable than this. And then ultimately, from the third rule, where we apply the rule for the situation having more than half field electrons in p orbitals, the larger the J value, the higher the energetic stability. So 2 is the most stable one. The next one is 1, and the least stable one among these 3 would be 0. So this order of the energy levels can be determined ultimately. So I mean, you see, probably for d orbitals, where you have magnetic quantum numbers from -2 to 1 and -2 to 2, or for f orbitals, it can become even much more complex. But the main idea is that you start from individual microstate. They are reorganized. Actually, each microstate is represented by each wave function. And the wave functions are making reorganization mathematically, that it includes some linear combination. And then you come up to the same number of states, but differently organized, which is in this case represented by different Thom symbols. And the nature does it to minimize the total energy of the system. Okay, thank you. That's it.